Alright, so we're in section, what is this, 9.2? Alright, so we're going to talk about ellipses. And we've started with all of our conic sections. We said they're conic sections. So let me grab a picture to show how our ellipse is related to the cone. Oh, we have to have the projector on, right? You guys can see automatically what I see? I told someone from one of the tech people that what I want is to have Google Glass and have all the students have Google Glass so everybody can see what I write, and then I can see if you're messing around on your computers at the same time, so I could turn your computers off with my Google Glass. That would be like that. All right, it'll be on in just a second. And everybody could have little earphones, so I could just be talking straight into your ear. Megan made a face. All right. Ellipses. So an ellipse. What we're doing to form an ellipse is we're taking a cone and we're slicing it with a plane so that the plane goes through both sides of the cone. And to contrast with how we made a parabola, the parabola of the plane went parallel to one of the sides. For an ellipse, the plane isn't parallel to either of the sides. So we get this kind of stretched out circle shape traced out along the surface of the cone. So that's where an ellipse comes from. So we can think of an ellipse as kind of a stretched out circle. But all of the conic sections are related because they're all traced out on the surface of a cone. All right, so we're going to start by defining our ellipse using our locus definition. So an ellipse is the locus of points. And a locus, again, is just a set of points that share some property. The locus of points where the sum of the distances from two fixed points and our fixed points are called the foci, plural of focus. Two fixed points called the foci. The sum is constant. So if we have an ellipse, let me grab I'll just draw a picture of an ellipse first. So I know my pictures are not beautiful and perfect, but we get the idea. So there's my ellipse. Kind of a sad looking ellipse, but all right, so there are our two foci of our ellipse. And we have this point on our ellipse, this point xy, and we're saying that the distance from the one foci, we'll call that d1, and the distance to the other foci, d2. We're saying d1 plus d2 is a constant. So that's how we're going to define our ellipse. What we would do is use the distance formula and have the sum of these two distances be constant, and we come up with our equations. We'll talk about the equations in just a second, but I want to talk about all the parts of the ellipse first. So everybody good with our definition? So just to kind of compare and contrast with circles, with a circle, our distance, the distance from a point to a fixed point, our center, is constant. That's how we came up with a circle. For a parabola, the distance from a point and a line were equal. So our point was the focus and our line was the directrix. Those distances are equal. In an ellipse, these two distances, the sum of the two distances is constant. So we're doing different variations on this idea with the distance and from the points and some different things, but they're all kind of tied together. All right, let's talk about some parts of an ellipse. So I have a picture here that I want to, not that one, that I want to grab. This one. Yes. So there is my ellipse. I'm going to stretch it out a little bit. All right. So the 2 points that are marked F are our two foci. We call this the axis that goes through the center. This is our center. The axis, the segment that goes through the foci and through the center of the ellipse is called the major axis. So from a vertex to a vertex, we have a vertex at the end of each major axis, or each end of the major axis. So our major axis goes through the center and through the two foci. At each end of that major axis, the long one, we call it major axis because it's the long one, is a vertex. The segment that's perpendicular to our major axis that goes through the center is called the minor axis. And at the end of the segment, the endpoints of the segment that make up the minor axis are called the co-vertices. We have two co-vertices here. The distance from the center to a vertex we're going to call A. The distance from the center to a co-vertex we're going to call B. And the distance from the center to a focus we're going to call C. So center to a vertex is A. Center to co-vertex is B. Center to a focus is C. I'm going to draw in one other segment here. I'll do that in red. Dotted line here. And I'm going to make this triangle here that goes from the center to a focus and then up to the end of a minor axis. This length is C. This length is B. A hypotenuse of that right triangle is A. So always for an ellipse, A squared equals B squared plus C squared. And if you draw that little triangle, that will help you remember that. This length is C, this length is B, and the hypotenuse there is A. So this hypotenuse from the focus to the end of the minor axis is the same length as from the center to the vertex. All right. The couple of other things about our ellipse before we write our equations. The center is at the midpoint of the segment that joins the foci. So it's halfway between the two foci. The center is halfway between the two vertices, or halfway between the two co-vertices. So we can find the center of our ellipse in several different ways. Using the co-vertices, using the foci, or using the vertices. Like this, A squared equals B squared plus C squared. That's going to be an important one to remember for ellipses. And that little triangle will help you remember. All right, questions on our parts? All right, so let's come up with let's write our standard form of our equations. We're talking about our standard form again. Standard form of the equation. So I'm going to say standard equation for ellipses. So we're going to do the same thing that we did with parabolas. We'll talk about a horizontal major axis and a vertical major axis. Just like with parabolas, we talked about a vertical axis and a horizontal axis. So let's talk about a horizontal major axis first. So let me grab my picture again. So there's my ellipse with a horizontal major axis. Just like we did with a circle, we're going to say that our center has coordinates h, k. For an ellipse, always a squared equals b squared plus c squared. And for an ellipse, a, the length of the major axis, or the distance from the center to the vertex, is always bigger than b, the distance from the center to the covertex. So a is greater than b for an ellipse. So a is the bigger number. Our equation, x minus h squared over a squared plus y minus k squared over b squared equals 1. So we can tell when our major axis is horizontal because the bigger number, a squared is going to be bigger, is under the x. So our bigger number is under x. Oops. So that tells us we have a horizontal major axis. Our center is at the point hk. The number a tells us how far right and how far left to move to get to a vertex. So our vertex is going to be at the point h plus or minus a, k. We're moving right and left from the center by a units to get to the vertex. B tells us how far up and how far down to move to get to the co-vertices. So our co-vertex, we can find our co-vertex at h, k plus or minus b, moving up and down from our center. Our foci, c tells us, let me label that again here. That distance is c. C tells us how far left or right from the center to go to get to each foci. So I'm going to go h plus or minus c, k. The length of the entire major axis from the center to a vertex is a, so the length of the entire major axis is 2a units long, and the minor axis is 2b units long. This is b, and that's b, so our minor axis is 2b units long. So this is our information for an ellipse with a horizontal major axis. A tells us how far from the center to go to get to the vertex. B tells us how far from the center to go to get to the co-vertex. C tells us how far from the center to go to get to the foci. The center is halfway between two foci, halfway between two vertices, or halfway between two co-vertices. Questions on our horizontal major axis ellipse? Notice this looks very similar to a circle. And in fact, if A equals B, if both of these numbers are the same, this length would be the same as that length, and we would get a circle. So this equation becomes the equation of a circle if A equals B. So ellipses and circles are very close relatives. All right, let's look at a vertical major axis. Is it warm in here? Yeah. All right, let me grab a picture of a vertical ellipse. And there we go. I'll have to bring my other fan in here. All right, everything is the same. All of our parts stay the same. It's just that I'm turning my ellipse. C is still the distance from the center to the focus. My major axis and minor axis, they still have the same names. The vertices and the co-vertices still in the same places. We're just rotating. So always for an ellipse, A is greater than B. So from the center to the vertex is always bigger. A squared equals B squared plus C squared, always for an ellipse. So our equation for our vertical major axis, y minus k squared over a squared plus x minus h squared over b squared equals 1. So if we look at our equation, the way we can tell if we have a vertical major axis, the bigger number is under the y. And we always have a plus sign here for an ellipse. We'll talk about what happens when we get a minus sign there next time. That gives us a hyperbola. Same situation here. Our center is still at the point HK. That doesn't change. Our vertex, each vertex, A tells us now, because my major axis is vertical, A tells us to move up and down from the center to get to the vertex. So it's going to be H, K, plus or minus A. I'm moving up and down now. The co-vertices. B tells us how far now, because our major axis is vertical. B tells us to move left and right to get to my co-vertices. So my co-vertices are going to be H plus or minus B, K. I'm just moving left and right. My foci, I move up and down C units to get to my foci. So H, K plus or minus C. My major axis is still length 2A. My minor axis is still length 2B. And that gives me all the information about my ellipse. Ellipses, the equations of ellipses, very friendly, almost as friendly as a circle. So for a horizontal major axis, I'm just going to pop back here really quickly. Horizontal major axis, my bigger number is under the x. A is always the bigger number when I have my equation written out this way. A squared is always b squared plus c squared. For a vertical major axis, A is my bigger number is under the y. And what we're going to do with ellipses is work with the vertices, the foci, the co-vertices, the center, to find out, to get information about our ellipse. And once we have the center A and B, we can make a pretty accurate sketch of an ellipse, because from the center we can go A units away and get the endpoints of my major axis, and from the center I can go B units away and get the endpoints of my minor axis. So that gives me a pretty good way to sketch the ellipse. All right, questions so far? Okay, let's look at a few examples working with this information from ellipses. We'll start with an easy one. Whoa. Yes, Steve. Ellipses. I'll talk at the end. I'll give a couple of applications, but the orbits of planets are elliptical. They're not actually circular. They're close, most of them, and the sun is at one focus. So the orbits of planets are elliptical. They'll design. Did you have? You did. Okay. I'll talk at the end. So you can make a room that has an elliptical either walls or ceiling, and if you talk at one focus, it reflects to the other focus. They call it a whispering chamber. So you can use the reflective properties of ellipses to design mirrors, so that their mirrors are elliptical. And then I just popped in my head like elliptical trainers. The reason they call them elliptical trainers is the path that the pedal takes is elliptical, and it's supposed to be a little smoother than circles. So, a couple of places. Yes.
So if you have when B is where A is where B, then and if you're saying what would be horizontal and A is
well, if so, the way we're defining the ellipse, we're going to say A is always the biggest number. So that just to eliminate that possibility, we just say that A is always the biggest number.
So if your B is bigger, we just put
Right. All right. So let's find we want the center, the vertices, and the foci of this ellipse. 9x squared plus 4y squared equals 36. Well, what do we need to do here to figure out our center, our vertices, and our foci? What's that? We want to. Juwan says let's divide by 36. We want to write it in standard form. In standard form, the number on this side of the equation, we always have x squared and y squared stuff on one side, and we have a 1 on the other side of the equation. So divide by 36. So we're going to write in standard form. So divide everything by 36, and I get x squared over 4 plus y squared over 6 equals 1. So there's my standard form. And now we can pick out our information. Where is the vertex, or sorry, where is the center of this ellipse?
9.
What's that? Did I divide wrong? 4 times 9. Thank you. So our vertex is at 0, 0, or sorry, center. I'm still thinking parabolas. Our center is at 0, 0, because we don't have nothing subtracted here. Our other numbers, what are the 9 and the 4 tell us? The 9 and the 4 tell us a squared and b squared, so which is a and which is b? 9 is a squared. A is always the bigger number. So a equals 3. B equals 2. So now I can find my vertices. My vertices are 3 units. One other thing we need to know Is this have a horizontal major axis or a vertical major axis? Vertical, because the bigger number is under the y squared. So we have a vertical major axis. So our axis is vertical. I'm going to say MA for major axis. So the A, the 3, is telling us to move 3 units up and down to get to the end of my major axis, to get to my vertices. So my vertices are going to be at 0 plus or minus 3. And then we need to find the foci. We know always for an ellipse, a squared equals b squared plus c squared. So we have 9 equals 4 plus c squared. So c squared equals 5 and c equals square root of 5. So that tells us to move 5 units, again up and down because my major axis is vertical from the center to get to my foci. So my foci are at 0 plus or minus square root of 5. And if we needed to, we could get a pretty accurate sketch of our ellipse by plotting our center at 0, 0, ends of my major axis at 0 plus or minus 3, ends of my minor axis at plus or minus 2, 0, and move left and right, and I would be able to plot out a rough sketch of my ellipse like so. Not a great sketch, but I said it was rough. So something like that. All right, questions on that example? All right, let's look at another one. We want the equation this time of our ellipse our center is at 0, 0. Our major axis is length 10, and our foci are at plus or minus 3, 0. So these problems, often when they give you this information like this, it's very helpful to draw a little sketch. It doesn't have to be a perfect sketch. It can just be some points. So what I usually do is I draw out a little sketch. Here's my center at 0, 0. My foci are at 3, 0 and negative 3, 0. All right, so we have almost all the information we need now. From our sketch, is our major axis vertical or horizontal? We have a horizontal major axis. We have all the information that we need to find all of our numbers. What does this major axis length 10 tell us? A equals 5. This is twice the 2A is the length of the major axis. So this tells me that A equals 5. What does this tell us? If these are the foci. C equals 3. Center to a focus is C. So C equals 3. I can start writing my equation because I know that A has to go under which coordinate with a horizontal major axis? A has to go under the x. So I can say x squared over, don't have to subtract anything because my center is 0, 0. X squared over 25 plus y squared over something equals 1. And from this, I can find B. I know that a squared equals b squared plus c squared. So 25 equals b squared plus 9. So b squared equals 16 and b equals 4. Plug that in here and I get 16. And there's my equation. Working with ellipses is almost like filling in the blanks. Plugging in the numbers, whatever numbers we need, we just plug them into the right place. All right, the next one we're not gonna go all the way through the example. I just we'll get started so we can see how to do the process, and then there's a couple last little things I want to talk about the ellipse. All right, next example. Everybody good with this one? And our process working with the ellipses is always the same. We use the coordinates they give us, and what we know about ellipses to find A, B, and C, and then plug them into our equation. Okay. For this one, we want to sketch a graph. So that's our setup for this problem. Sketch a graph of 25x squared plus 9y squared minus 200x plus 36y plus 211 equals 0. So we want to sketch a graph of that thing. So how do we need to start? What do we need to do? We get to complete the square. So I'm going to group my x terms together. 25x squared plus or minus 200x. So I'll group those together. Plus 9y squared plus 36y. Group those together, and I'm going to put equals negative 211 on that side. Now before I complete the square, what's our next step before we complete the square? We want to factor out this 25 and this 9. We don't want that in there when we complete the square. So I'm going to write this as 25 quantity x squared minus 8x plus 9y squared plus 4y equals negative 211. And now we're set to complete the square. We'd complete the square on the x part, complete the square on the y part, and we would remember, because we've done this enough times, that when we complete the square we have to distribute the 25 to whatever number we add inside here. We have to distribute the 9 to whatever our term is in here, and we have to add those two numbers after we distribute the 25 and the 9, add them to this side. Yeah. So what would happen, let me go back here really quickly, that's a good question. We would do that one like we did this one. So we would have a number here, we'd have a number in front of our x term, a number in front of our y terms, and some other number, big number on this side. And we divide by the number on this side, so we'd get a 1 there. And then we'd end up with different numbers under the x and the y. Back, this one. So if we divide, whatever number we divide by is going to make, you're saying the number in the denominator here is going to be bigger. Yep, so that's a good, so just looking at this, we have a lot of information even before we complete the square. Yeah, John. Yes, so that's another, very good, very good. So we see that we have a different coefficient in front of the x squared part and the y squared part. They're different. That will tell us that it's, and we have a plus sign. So if these two numbers were the same, and we had that plus sign, then we'd have a circle. If we end up with a minus sign here, then we'll end up with a hyperbola, and that's what we'll talk about next time. And when we complete the square, it turns out that this turns into x minus 4 squared over 9 plus, and just like Daisy said, we end up with a vertical major axis. Y plus 2 squared over 25 equals 1. And then to sketch our graph, we know our center is at 4, 2. Our distance from the center to the vertex is 5. The distance from the center to the co-vertex is 3. And we can plot those points and sketch out our ellipse. All right. One last piece of information. We're going to define the eccentricity of an ellipse. E equals C over A. And the eccentricity tells us how much different from a circle our ellipse is. And our eccentricity is going to be between 0 and 1. If it's close to 0, if the eccentricity is close to 0, then C and A are close to being the same. So our focus and our vertex are kind of, that length is the same, and we end up with something that's close to a circle. If the eccentricity is close to 1, then the ellipse is more stretched out. So this tells us how stretched out our ellipse is. And just to reiterate, orbits of planets are ellipses. So that's one place where ellipses show up. And the eccentricity tells us, like the eccentricity of Pluto's orbit would be close to 1 because it goes way out, way back in, so it's not as close to the circle as Earth's orbit is a little more circular. And whispering chambers, have any of you ever been in a whispering chamber? They're pretty cool. I've been in last summer, 2 summers ago, there was a piece of art where I was, and you would stand, and the piece of art was 2 big sheets of metal, like this. So you'd kind of walk inside, and if you were standing at one focus, someone else could stand at the other focus. You could talk this way, very quietly, and it sounded like the person was standing right next to you talking.
Isn't that in our library or something?
Is there a spot in our library that's that way? I know in there's Whispering Gallery in, where is it? In the White House? It's like in the National Gallery, something like that. There's a whispering chamber. There's at my house we have a lampshade that's kind of elliptical shaped, and when someone talks, when you stand in just the right place, you can hear your voice coming in your other ear, and it's really strange. So I thought that was kind of good. Anyway, homework. All right, there we go.